So I knew her then as a physics major, but as she came to the end of her course in fourth year, I guess it was the summer before fourth year, wasn't it? She asked me if I would teach a special summer course on astronomy. And I was a little surprised. I never had a student ask particularly about astronomy, but I knew something about it, so I said, okay, we'll put something together, see if you could get some companions. And you did. You got a bunch, I guess, of your friends. I don't know how much you twisted their arm, but anyway. So during that summer, we went through kind of a survey course of astronomy, which was easier to do because she had the background in physics. So it was really astrophysics, we could say. But that was a beginning of something I never realized would turn into this. So after that, then she went on for graduate studies, Princeton, and in Princeton got involved in really serious astronomy, astrophysics, as it would be the application of physics to the stars, and finished her work there. And then became well known because she was interested in applying relativity, the 1915 publication of Einstein, general relativity we call it, it's actually a theory of gravity, to the galaxies equivalently, or to the stars, let's just say that, okay? Trying to show its applicability. And so she became well known for that, and I guess even had national exposure due to that. Now she's working in a special institute in Chicago, which wants to look into fundamental questions like that. I mean, fundamental questions of physics, fundamental questions of science, wanting to see, like, how did the world begin? What is the Big Bang? Was there only one Big Bang? Could there have only been one Big Bang? Et cetera, et cetera. So the Kavli Institute is very much interested in theoretical science, trying to answer some basic questions, we would say, in what we call today cosmology. So Reinabelle is gracing us here with her presence. She has been earlier in Palawan, right? And so we're glad that she's here to share with us some of the science and get us interested in the way science is moving. And then, of course, if we're very nice to her, we'll have her come back after she finishes Chicago, right? So she can enjoy our beautiful air and mountains and stuff like that. So with that, Reinabelle.
Thank you, Father Dan, and thank you everyone for coming. It's a pleasure to be here. It's a beautiful room actually, because we see all around us the view and the skies. Very cloudy, but let's hope that the clouds clear. Maybe we'll see some stars tonight. If you go to a really dark place high up in the mountains, probably if you go to Mount Akbar, one of these mountains, you'll see the Milky Way. All the stars, bright. If you let your eyes be accustomed to the dark, you start to see more stars. And this is a very particularly dark sky in Chile, in the south. And you see through the center of the Milky Way. And that's why they put a telescope here. It's a dark place. And you see, this is where we live. We're right in the middle of the Milky Way. And today, in the next hour or so, we're going to talk about the birth and death of the Milky Way. So let's begin our journey. I framed this talk with 3 questions. That's actually the title of this painting by Paul Gauguin. These 3 questions are questions that people have been asking since they were people. They are fundamental questions. Number 1, what are we? Who are we? Sino ba tayo? Kinsa ta? Number 2, where did we come from? Saan tayo galing? Asa tayo gikan? Pwede na? and then, where did we come from? And we ask, where are we going? Asa tayo padulong? Saan tayo papunta? And we can ask this, some people can ask this for ourselves individually, but as a people, as scientists, we are starting to answer these questions, to ask and answer these questions from science. So, what are we? Who are we? What is our place in the universe? Where did we come from? Where did the Earth come from? Where did the galaxies come from? Where did the universe come from? And where are we going? What's going to happen to the Earth, to the Sun, to the galaxies, and to the universe far, far in the future? And I'm going to share with you the answers we have from the latest research in astronomy and cosmology, in this case focusing on galaxies, on the Milky Way. So let's start with the first question. What are we? Where are we? Who are we? What is our place in the universe? And I'm going to show you a video that starts from the Earth and we travel out to the farthest reaches of space, the universe, to see where we are, a telescopic view of the universe. So we'll start the video. We start in the surface of the Earth. This is the Himalayas mountains, not very different from the mountain ranges we have. And then we zoom out. So let's play this. So from the surface of the Earth, it looks flat. Right? For a long time, people thought that the Earth was flat. But then Magellan went around the Earth. And also now we can just see from our satellites, we've imaged that we are living in a ball of water and land. And this is where we live. This is our planet. You call it the Earth. And you can see the Philippines, cloudy. And this is our home, essentially. Everyone you know, everyone who lived, everyone who ever lived, everyone who ever lived in the near future will be here. Now, these orbits, these green lines, are the orbits of artificial satellites. So we've sent satellites to go around the Earth, to image the Earth, and also for our GPS satellite, we can now get directions. And these are coming from the satellites, beaming the signals down. Start to see the sun, our parent star. And as you move out, you start to see the moon's orbit, right? And then now the orbits of the planets. So further in, they have Mercury, Venus, and then Earth. And as you go out, Mars, the asteroid belt, Jupiter, Saturn, Reyes, Neptune, Pluto. It's no longer a planet, but it's there. And that's our solar system. That's our neighborhood. As you move out, you see they now put in the sun's true brightness. And as you move out, it now just looks like all the other stars in the galaxy. You can't even tell where the sun is. So we are actually in a pretty average place. As you move out, you see now the center of the Milky Way. We are about in one of those arms, about 2/3 away from the center. And that's our galaxy, that's the Milky Way galaxy. Now you start to see these green dots. Each green dot is a galaxy just like our own. And we have imaged them and mapped them in space. We have millions of galaxies. And these areas are also full of galaxies, but they're just, we haven't looked at them. So we have now this map of the universe. And even further out, we can see these quasars, these very bright, actually black holes that are gobbling up matter. And so we can see them out very far. So again, you see that structure until we reach the farthest reach of space, which is light from shortly after the Big Bang, 13.7 billion years ago, is the cosmic microwave background that we see all around us. And that's this glowing ball. And that's the known universe. The incredible thing about this video is that everything you saw, almost everything, everything you saw is an observation, is a measurement, is something we know. Do you know what's the only thing that's not real here? Can anyone guess? If you remember, we showed image of the Milky Way, right? But that image is not an observation, right? It's an artist's impression. Why? Exactly, yes. We cannot take a picture of the Milky Way because we're in it. So it's like it's a plate, we're inside the plate. So we see all the stars, but we cannot take a picture, top view picture. But we can see galaxies around us, and they look, and then actually we can map what it would look like based on the stars that we see. So that is the best guess of what the Milky Way looks like. But all those points are actual observations of galaxies from the sky. And even this cosmic microwave background is also observation. So we live in a time where we know so much. We know our place in the universe more than just 10, 20 years ago. And we can make these kinds of videos. So we have our answer, rough answer. Where are we? We are people living in a planet we call Earth, which is one of 8 going around a star we call the Sun, which is just one of 100 billion stars in our galaxy, because the galaxy is made of all these stars. But this galaxy, which are only called the Milky Way, is just one of 100 billion galaxies that make up the universe. And that's our picture. That's our place in the universe. And when you think about it, when you first hear about it, or when you just even contemplate about it, it makes you feel really small. Because you're just one speck, this big, big universe. But at the same time, it also makes you feel awe and power. It makes you feel powerful that we, however small we are, can know about the universe, can reach out to the farthest limits of the universe and learn about it through our instruments, through our telescopes, through our science. And so it's always that double feeling. Being small but also big, that we can learn about the universe, and we are actually connected to the universe. So that's our jumping off point. Go to the next question. Where did we come from? Where did all these galaxies come from? And so we start from the beginning. I said, Big Bang, the beginning of the universe we know, was 13.7 billion years ago. Not that long ago, just 14 billion years. And we have captured a big picture of the universe. Meaning, this is light just right after that. Meaning, it's actually around 400,000 years after the Big Bang. So this is what it looks like. This is called the cosmic microwave background. Because it's in microwave, meaning it's light but in long wavelengths, the same that you use in the microwave oven to heat your food. But when we have a detector that can detect microwaves and we point it to different parts of the sky, we see that some places are hotter, a bit hotter, some places are cooler. And that's the coloring here. So we have blue, I think is a bit cooler, and red is a bit hotter. But the difference between these blue and red spots are very, very small. It's 1 in 100,000. 1 part in 100,000. So it's 0.00001. So that's the difference between these spots. But we can measure them. It's very small. What this actually tells you is that in the beginning, it's all uniform. It's the same everywhere. Just atoms spread around, hydrogen atoms spread around. And there are just very tiny differences between different locations. But essentially, it's the same everywhere you look. So there were no galaxies, no planets, no stars, nothing, right? But today, we know we live in a planet, we live in a galaxy, and even more than that, the universe is filled with galaxies, as you said. And this is a picture of just one patch of the sky that looks dark. And just look at the place and it's dark. But if you look at it for a long time with a powerful telescope, this is from the Hubble Space Telescope, which is a telescope we sent to space. And it looked at one part for a long, long time and essentially took a picture, a very long exposure picture. You see these, it's just filled with galaxies. So for example, this one is a galaxy that looks much like the Milky Way. It's a spiral galaxy. And then you have these types of galaxies that are redder, and they're called elliptical galaxies. There are basically two types of galaxies. Let me see. So again, here, this is like a tiny, tiny spiral galaxy, Milky Way. And this one is also the same, but it's edge-on. It's this way. Yeah, we see it this way, so we see it flat. And this one, we see it face-on, so we see it in a beautiful spiral galaxy. And then what are these? What do you think these are? With the spikes. These are stars. Yeah, these are just stars that happen to be in that field. Right? So these are stars in our own galaxy. They're close. But all these other stars, all these other galaxies, each galaxy here is made of 100 billions of stars. So this is the universe today, meaning after 13.7 billion years, we have all these galaxies. And as scientists, as astrophysicists, we want to understand how that happened, how the universe evolved from the beginning with no galaxies to today with all these galaxies. And more than that, we want to explain why they look this way. And this is ongoing research. We have some understanding, but it's not complete. That's why I have work, is to try to understand why these are. And again, this is another way of looking at the galaxies. This time we have 3D information. So not only do we know where they are in the sky, we know their location in the sky. And so this is a map. We are here in the center. And these are all galaxies, all the little dots. So these are nearer to us. These are farther away from us. Right? And what you'll notice here is that there is structure. Structure, it's been called a cosmic web because it sort of looks like a spider's web. Meaning, let's see, there are places where there are lots of galaxies. For example, here there's what we call a filament. They are all bunched up together. Here again, and also of course here. And then on the other hand, you have places where there are no galaxies. So these black places here, in between the filaments, they're called voids because there's nothing there. There's nothing there. And so there's this structure, and we also want to explain this structure. And actually, this structure has been explained in the past 10 years, and I'll show you how. And then, of course, these places, we just haven't looked. Okay? The question is, why haven't we looked here? Can anyone guess? So you can imagine we are in the galaxy. It's like a plate, right? So what we do is we look up and down the plate. Because if you look here, there are too many stars. Yeah, there are too many stars. But of course, we believe it looks the same. You can fill this in. It should be the same. Because everywhere we look, it looks sort of like this. It's the same. But just too many stars to look here. Yeah. So during those times, we study the stars. And then during the other times, we study the galaxies. Yeah. And we study the stars again, we study the galaxies. That's how we do it. Alright. So that's the basic picture. Again, this is just another way of looking at it. Now this is time. This is the beginning, the Big Bang. And just 400,000 years after, you have the imprint from the cosmic microwave background. And then there were no stars. And then at some point there were the first stars. And then the galaxies formed. And then today we have a universe of galaxies. Yes, and also, yeah, the background here is that the universe is expanding. And I haven't really talked about that. But the universe is also expanding at the same time this is happening. Right. So the question is how to build a galaxy. Of course, the question is how to build all the galaxies, but let's start with one galaxy. And we'll do it in 3 steps. Right. So step number 1, build the universe. Where you will put the galaxy, right? So, build a universe, we need the ingredients, we need the recipes, like a recipe. So, if you're going to make a cake, you need how many eggs, how many flour, and then you mix it all together. So, to build a universe, we need to know what its components are. And in fact, we figured it out. This is a pie chart of what the universe is made of. You'll first notice here the atoms. Atoms are everything we know, everything we're made of. All the stars, the earth, us, the periodic table of elements in chemistry are all here. And it's only 4% of the universe. We're not even the dominant stuff in the universe. It's also very humbling. The dominant stuff in the universe is something we don't see, so we call it dark matter. Dark matter. And it's 23%, so it's about 5 times more mass, more mass than the atoms that we see. So this actually, the dark matter dominates the evolution of the universe, as I will show. And then you have this big chunk, about 3/4 of the energy of the universe, we think is something that's making the expansion of the universe accelerate, become faster and faster. But to be honest, we don't know what it is. So we're calling it dark energy. Right? But this is an active area of research. What other things could it be? That's also part of what we worked on to test general relativity. Because of general relativity, the theory of gravity is wrong. It could be something different that's making the expansion accelerate that could explain that, and you don't need dark energy. So this is still very, very mysterious. But in fact, if you assume that there's a dark energy, you can explain all the observations that we have. So this is the current picture of cosmology. You have dark energy, dark matter, and the atoms. And that explains what we see. So this is what I will show. It's a computer simulation. So it's another video, but it's from a real scientific computer simulation where you put in dark energy, but this just makes it makes the universe expand. It controls that, and then you put in dark matter, and then we will see the universe in a box. Okay. So the atoms are small, so in the beginning you don't include the atoms. Look at that, yeah. So you build the universe, you put the dark matter in, and then you turn on gravity. Because gravity is what affects the evolution of the universe as a whole. But gravity, you know gravity, right? Gravity is what keeps us in the ground. And if I drop this is an expensive thing, so I won't, it will fall. Just like the apple that Newton saw, allegedly. and the moon and everything. So this is why how the Earth rotates around the sun and the galaxy and everything. So what happens is that gravity essentially just wants to attract. So it's an attractive force, so it attracts everything. And you will see it in action in this simulation. So this is the computer simulation. It's just a box, and it's colored by the density of matter. So you see dark places are just slightly have less matter, lower density. And then here it's like pink or red, where you have matter. And then when I play this video, you let time run and gravity will work. So watch what happens. It's very slowly. Oh no, it's not moving yet. Let's do it again. Okay. So time is running. Very slowly, you see gravity acting. So where there are places where there's more matter, it attracts the matter around it, and it starts to grow. And then you see these filaments start to grow. And then the places where there's initially less dense matter, the matter is pulled away from it and it became bigger. And then you get these points. So the rich get richer, the poor get poorer, and in the end, you have the cosmic web. Exactly, really, it's exactly like what you see in the universe. In the map that I showed earlier, it looks like this. And then in the computer simulation, we are able to reproduce the observations, and that's why we know that we understand what happened. This is how science works. Do you want to see that again? Yes? It's short, so let's do it again. So in the beginning, again, it's smooth. And in fact, we know that from the cosmic microwave background that I showed earlier. Those red and blue spots, and I said it was 1 part in 100,000. So those are the initial differences. And those differences were magnified by gravity to what we see today, the cosmic web we see today. And so we have this nice picture of from going from a smooth universe to a clumpy universe today. So that's in one picture, start out very smooth, over time gravity acts, and you get this filamentary structure, clumpy structure today. And it matches what we see in the universe. And in fact, that's how we know how much dark matter there is, for example. Because if you make it more, this will look more clumpy. So, for example, that's what actually happens, is you match this with observations, and you learn more about the components of the universe. And so, we have explained the general structure, but this is just the dark matter, so no galaxies yet. And that's what we need. So the final step is to add the atoms. And that's the hard part. In fact, that's what we're working on right now. But what I'm going to show you is a recent computer simulation that shows a galaxy forming. So now include gas and stars, and you need to put in the laws of physics, and then see what happens. So this is the beginning of the video. Again, it's smooth. But now this is very small, so zoomed in. These are clumps of gas. And you see they're streaming in through filaments that are the filaments of the dark matter we saw earlier. But as they form now, they start to form a disk. And this says about 10 billion years ago, there's this last major merger, and you start to form the disk of a spiral galaxy like the Milky Way.